The November wind cut across Aberdeen proving ground with teeth, and the thermometer was dropping fast. It was November 15th, 1943, and the mercury had already dipped to 34 degrees. The Maryland landscape stretched out flat and desolate around them. A vast testing facility sprawled across frozen ground like the world's largest mechanical graveyard. Rusted tank hulls, abandoned artillery pieces, and gutted truck frames dotted the terrain, casualties of America's relentless engineering trials. Staff Sergeant Mike Kowalski stood with his hands jammed in his jacket pockets, watching as workers unloaded something from the transport truck. 1,740 pounds of enemy machinery. A single Kubelwagen, the German answer to the American Jeep, was about to become the most scrutinized piece of automotive engineering at Aberdeen. Kowalski had spent 15 years on the assembly lines of Detroit, Ford, Chrysler, everywhere they built cars. He could read an engine like a book, could diagnose problems by sound and touch that would leave other men scratching their heads. His hands carried the memory of thousands of vehicles, and they were ready for this one. The vehicle emerged from under its olive-drab covering like some carefully guarded secret finally being revealed. Even sitting still on the concrete pad, the Kubelwagen possessed a certain elegance. The American Jeeps nearby suddenly looked crude and clumsy by comparison. This was supposed to be the product of German precision, German discipline, German engineering genius. Intelligence photographs had shown it to Kowalski months ago. Tactical reports from North Africa described how effectively these machines had moved German officers across contested ground. This was Volkswagen's masterpiece, the automotive embodiment of everything Americans kept hearing about German superiority. But the brass wanted proof. They wanted numbers. They wanted a complete technical evaluation that would either confirm or contradict everything the War Department had been assuming about the enemy's industrial capabilities. Kowalski popped the hood for the first look inside. What he saw stopped him cold. The engine compartment held something that looked almost fragile. An air-cooled power plant with flat cylinders arranged with almost delicate construction. Nothing like the robust cast-iron blocks he knew from his Detroit days. This was minimalist, stripped down, almost apologetic in its simplicity. He checked the specifications sheet twice. 25 horsepower. The American Willys Jeep, sitting just 50 yards away, produced 60. That was more than double the output. Even his father's old Model A from the 1920s had generated more power than this supposed German wonder weapon. Technical Sergeant James Patterson arrived from the dynamometer building, his breath visible in the cold air. 5 years at General Motors had taught him methodical precision in everything. He carried a clipboard thick with testing protocols, and his expression carried the weight of serious military business. "War Department wants the full treatment," Patterson announced, his voice carrying real authority. "Complete technical analysis, everything from power curves to maintenance requirements, manual TME 803, the whole thing." Kowalski nodded and reached for the hood release. His callous hands understood automotive engineering in a way that didn't need formal schooling to work. He could diagnose transmission problems by listening to how gears shifted. He could identify bearing failures through vibrations that others would never even notice. 15 years had taught him things no classroom could. Corporal Tommy Chen joined them, already holding his slide rule. Chen was Berkeley educated, a mathematician by nature, someone who spoke the language of pure numbers and quantifiable relationships. He studied the Kubelwagen with the intensity of someone solving an equation. "Displacement, 985 cubic centimeters," Chen announced, translating German specifications into American measurements with practiced efficiency. His slide rule moved with precision. "That's roughly 60 cubic inches, peak power at 3,300 RPM. Chen's calculations continued, converting metric into familiar imperial units. "Power-to-displacement ratio is terrible," he said flatly. "Worse than most civilian vehicles." Patterson made careful notes, his General Motors training demanding documentation of every observation. This wasn't mere mechanical curiosity. The War Department needed comprehensive data about enemy capabilities. American commanders were making tactical decisions based on assumptions about German technical superiority. If those assumptions were wrong, the implications stretched far beyond this single testing facility. Major Robert Sterling arrived as they were beginning their preliminary inspection. His pressed uniform and polished brass marked him as someone from the institutional military establishment. 20 years of service had taught him to respect European military traditions, and West Point had emphasized understanding enemy capabilities. "Gentlemen," he announced with formal courtesy, "this evaluation carries significant strategic importance. German automotive engineering has long been considered among the world's finest. We need to understand exactly what advantages their equipment provides." Kowalski bit back his first response. Years of military discipline overrode his working-class instincts. The Major's expectations were crystal clear. They were supposed to find evidence of German technical superiority to quantify the engineering advantages that explained battlefield success. But the evidence sitting before them told a completely different story. The engine's construction revealed design choices that prioritized different values than American automotive engineering. Detroit built for power and durability. The Germans had optimized for fuel efficiency and manufacturing simplicity. The air cooling system eliminated the weight and complexity of liquid cooling, but at the cost of thermal management under stress. The rear-mounted configuration improved traction in snow and mud, yet created maintenance access problems that would plague field mechanics. As afternoon shadows lengthened across Aberdeen's testing ground, Kowalski found himself staring at a machine that challenged everything he'd believed about German engineering supremacy. This wasn't the automotive masterpiece that intelligence reports had promised. It was a compromise, elegant in certain ways, but fundamentally limited by design choices that prioritized theory over practical battlefield performance. The real testing would begin tomorrow, when dynamometer measurements would replace subjective impressions with hard numbers. But already Kowalski sensed they were about to uncover something that would shake the War Department's fundamental assumptions about enemy capabilities. The dynamometer building hummed with electrical energy as Patterson set up the massive testing apparatus. 4 days of preparation had transformed Aberdeen's primary automotive facility into a precision measurement laboratory. Cables snaked across the concrete floor like mechanical arteries, connecting German engineering to American scientific methodology. Kowalski guided the Kubelwagen onto the dynamometer rollers with practiced precision, feeling the vehicle settle into the testing cradle that would hold it motionless while its wheels spun against calibrated resistance. The morning air carried the sharp scent of industrial lubricants and electrical equipment, familiar aromas that reminded him of Detroit's proving grounds where peacetime automotive dreams had once been tested against mathematical reality. "Beginning baseline power measurement," Patterson announced, his voice carrying the methodical tone of someone who understood that sloppy data undermined credible conclusions. 5 years of General Motors engineering discipline had taught him to approach every test with laboratory precision, documenting variables that less experienced technicians might overlook. The War Department demanded numbers that could withstand scrutiny from Pentagon engineers who had never seen combat but possessed absolute faith in quantified analysis. The Kubelwagen's engine note changed as Patterson gradually increased the dynamometer load, simulating the resistance of hills, headwinds, and battlefield conditions that would challenge the vehicle's capabilities. At idle, the flat-4 engine produced a distinctive sound, smoother than American inline configurations, but somehow less substantial. Like a sewing machine compared to a bulldozer. The air cooling system's fan created a constant whisper that seemed almost apologetic compared to the confident rumble of liquid-cooled American engines. Chen positioned himself beside the instrument panel, with his slide rule ready. His Berkeley education provided the mathematical framework needed to translate raw measurements into meaningful comparisons. Numbers represented truth in its purest form, immune to propaganda, cultural bias, or wishful thinking. "Peak torque at 2400 RPM, he called out, recording figures that would soon travel to Washington in classified reports. Maximum power output, 25.3 horsepower at 3,300 revolutions per minute. The implications hit Kowalski like cold water. Everything they'd been told about German engineering superiority was sitting on this dynamometer, and it was producing barely enough power to pull itself uphill. Those measurements weren't rough estimates or preliminary guesses. They represented exact data from German automotive engineering at its absolute finest. The Kubelwagen was working precisely as intended, delivering every bit of power that Volkswagen's designers had promised it would produce. The issue wasn't mechanical breakdown or neglect. German engineering had been optimized for completely different goals than what American vehicle designers were chasing. Patterson clicked his stopwatch as acceleration testing began, measuring how fast the Kubelwagen could go from 0 to 30 miles per hour. 26 seconds ticked by before the speedometer hit that target speed. For a military vehicle meant to move quickly across battlefields, that was painfully slow. The Willys Jeep sitting nearby could reach 30 miles per hour in just 11 seconds, moving with the kind of force that showed Detroit's philosophy of raw mechanical muscle. The weight numbers told an interesting story about how differently the Germans and Americans thought about vehicles. Chen ran the calculations. The Kubelwagen came in at 1,140 pounds, while the Jeep weighed 2,453 pounds. They'd managed to cut 700 pounds of weight, yet the American vehicle still had the better power-to-weight ratio by a substantial margin. Major Sterling stood on the observation deck of the testing building, trying to hide his growing worry about what these numbers meant. His decades in uniform had taught him to respect European engineering traditions. But the information coming out of Aberdeen's facility was shaking his basic assumptions about whether Germans really were technically superior. If German vehicles had such poor performance numbers, why were German forces winning battles across so many different countries? Patterson shifted through the Kubelwagen's 4 gears as he tested the transmission, measuring how the power multiplied at each gear ratio. The German transmission shifted with silky smoothness, but it lacked the tough mechanical strength that American engineers had built into their designs for soldiers who would abuse the vehicles under combat conditions. That delicate precision felt almost fragile compared to the solid, dependable American transmissions built to handle punishment from 19-year-old drivers fighting for their lives. Halski stood nearby, thinking about the mechanics in Germany who had to fix these vehicles while bombs fell around them. His 15 years working assembly lines had shown him that beautiful engineering meant nothing if it couldn't survive real abuse. The Kubelwagen's sophisticated design would become a serious problem when field mechanics needed to repair it with whatever tools they had available while artillery exploded nearby. The cooling system tests produced the most disturbing findings of the entire evaluation. Patterson watched as engine temperatures climbed on the dynamometer, seeing coolant heat levels that would have shut down any American liquid-cooled engine immediately. The air cooling system's weakness became obvious when the engine had to work hard for long periods. It handled everyday civilian driving fine, but the constant high-power demands of combat pushed it past its limits. Temperature climbed beyond what was safe when the engine had to deliver steady power, Patterson reported. His engineering training let him explain what those numbers really meant. "This engine can't keep working at military performance levels when it's pushed hard in combat," he said. Chen's slide rule flew across his calculations as he compared how well the German air cooling worked against American liquid-cooled engines. His numbers showed uncomfortable truths about design choices that looked good on paper but failed when pushed hard in real fighting. The cooling couldn't handle military demands during actual operations, he concluded. His mathematics confirmed what Halski's instincts about engines had already told him. As the morning tests finished, Halski looked at the measurements that would soon reach Pentagon offices where military leaders made decisions based on what enemy vehicles could do. Every single number said the same thing. American automotive engineering had won through a different approach, choosing power and strength over elegant designs. The question haunting him went beyond just mechanics. If American soldiers had better equipment than the Germans, why were they struggling so much? Aberdeen's test hill rose on the eastern part of the proving ground, a stark concrete challenge to any engine's capabilities. The 12-degree slope represented the kind of terrain that separated real military vehicles from pretenders. The November morning was cold and clear, but soon the engines would be roaring as the vehicles climbed past their comfort zones. Halski prepared to put the Kubelwagen through a test that would show whether German engineering could turn those horsepower numbers into actual mobility on a battlefield mountain. A quarter-mile of flat ground came first, letting vehicles build up speed before they hit the steepest part of the hill, where physics would eliminate every advantage except sheer mechanical power and how well cooling systems worked. Patterson had set up temperature sensors at several spots along the route, building a complete system to measure exactly how the German air cooling performed when the engine worked as hard as it would in mountain combat. Halski shifted into first gear, and the Kubelwagen started its climb up Aberdeen's artificial mountain. The flat-four engine shifted from quiet ticking at idle to strained groaning as the slope demanded more power than Volkswagen had designed into it. By the 500-foot mark, engine temperature gauges were showing thermal stress that would have triggered warnings in any properly designed American vehicle. The cooling fan screamed like it was fighting for its life, trying to throw off heat that was building up faster than the aluminum fins could release it into Maryland's cold November air. Chen watched the vehicle climb using binoculars, his calculations running the math on how much power the vehicle needed versus how much it was actually able to produce. The equations revealed something bleak and obvious. Every degree of incline multiplied the workload the engine faced, turning the Kubelwagen's 25 horsepower from barely adequate into hopelessly weak for climbing even gentle hills while loaded down. Speed dropped below 15 miles per hour, he called out, his voice cutting across the test area. Engine heat is beyond safe ranges now. The Kubelwagen's transmission hunted between gears as Halski fought gravity's relentless math. German engineers had focused on fuel economy and simplicity in manufacturing, but staying alive in combat required steady power that this air-cooled engine just couldn't produce without overheating. At 800 feet, the temperature needle was entering the zone where the engine would break rather than maybe break. Patterson's radio crackled with numbers that proved what Halski could feel through the pedals and steering wheel. The Kubelwagen was hitting the wall of what it was capable of doing, and it was facing a hill that American Jeeps drove up every day without breaking a sweat. Engine temperature is at 210 degrees Fahrenheit now, Patterson said, knowing those numbers represented the gap between what German designers hoped for and what soldiers actually needed. Immediate shutdown recommended to save the engine, he advised. But Halski kept going, knowing this test meant something bigger than just measuring a vehicle. It was testing whether German engineering superiority was real or just an assumption everyone had accepted. The engine's cries grew louder and more desperate as aluminum pistons expanded beyond what they were built for, creating gaps that hurt the compression and drained more power away. Steam started pouring out from under the hood as the oil approached temperatures where it would stop protecting the engine from friction damage. Major Sterling watched from his bunker as this symbol of German automotive excellence struggled up a hill that milk trucks climbed past every day without any trouble. His military schooling had taught him to respect European engineering, but what he was seeing challenged ideas that had guided American military strategy since the war began. If German vehicles had such serious limitations, how had German forces been winning in so many places? At 900 feet, the Kubelwagen ran out of power and quit. Halski felt the engine lose its ability to push the vehicle forward as heat overwhelmed everything, leaving him rolling backward down the hill while the German precision engineering vented scorching air everywhere it could. The vehicle that intelligence had called militarily effective had failed at climbing a slope that represented normal battlefield requirements, not extreme ones. Comparing it to an American Willys Jeep made the difference in engineering philosophy crystal clear, and that difference meant real consequences in actual fighting. The Jeep attacked the same 12-degree slope with mechanical confidence that showed Detroit's belief in having more than enough power and cooling systems built tough for long hours of hard work. Where the Kubelwagen had struggled and died, the American vehicle climbed with reserve power that could handle even steeper hills with full combat gear aboard. Chen's slide rule gave numbers to what they were seeing. The German vehicle can climb maybe 8 degrees with a full load, he announced, his calculations turning heat limits into tactical constraints that would affect how far and fast vehicles could move across European terrain. The American Jeep can handle 27 degrees under the same conditions, a capability gap that translates directly into superior battlefield mobility. Through the afternoon, word of the Kubelwagen's failure spread across Aberdeen like gossip in a small town. Test workers from other projects stopped what they were doing to see German automotive engineering get taken apart piece by piece using American measurement systems. The vehicle that propaganda posters had shown as a symbol of German technical brilliance sat cooling in the Maryland air, all its limitations exposed by math that didn't care about national pride. The traction test delivered the final blow as Holsky drove the rear-wheel drive Kubelwagen into Aberdeen's sandpit, where controlled conditions would measure how it handled grip and movement on terrain like what soldiers actually faced. 4 inches of loose sand, barely enough to bother a civilian car, completely stopped the German vehicle. Its narrow tires and weight distribution created a situation where small ground obstacles became showstoppers for mobility. Patterson recorded everything with exact precision. Understanding these numbers would reach Pentagon decision-makers evaluating German capabilities. The same sand trap that American Jeeps could handle at 18 inches had shut down the German vehicle at 4 inches, showing design choices that prioritized elegant theory over practical fighting capability under conditions that soldiers faced regularly, not in extreme situations. In Aberdeen's unheated maintenance shop, the precise sounds of taking things apart filled the December cold as Holsky started the final test phase that would show whether German engineering made up for its performance limits through easier repairs and better field service options. The bitter winter cold had turned the workshop into an environment like where combat mechanics would fight to keep vehicles running under fire and terrible weather. The basic oil change began what Patterson called comparative maintenance evaluation, timing everything against identical work on American vehicles to measure the hidden costs of German design complexity. Holsky started his stopwatch as he looked for the Kubelwagen's oil drain plug. Immediately hitting the first sign that German engineers had chosen elegant theory over practical field service. The drain valve sat tucked behind a protective skid plate, accessible only if you approached from multiple angles with the right tools. Kowalski had been at it for 15 minutes without getting a single drop of oil out. His breath fogged in the frigid air as he wrestled with access panels that looked like they'd been designed by engineers who'd never actually changed oil in combat conditions, let alone during peacetime. His 15 years on Detroit assembly lines had taught him that complexity in maintenance was the enemy of readiness. Every minute wasted on servicing meant less time the vehicle could spend combat-ready, meant vulnerability creeping in while mechanics were tied up with their wrenches. Patterson methodically documented each step, knowing these measurements would shape how the War Department approached maintaining captured German equipment. His General Motors background gave him perspective on design choices that looked impressive on paper, but created absolute nightmares for field mechanics with limited tools and impossible conditions. German design philosophy puts component protection ahead of service access, he observed, watching Kowalski struggle with fasteners that demanded specialized tools rather than the standard military wrenches any soldier could find. An oil change consumed 12 minutes on an American Jeep. The same task on this Kubelwagen ate up 45 minutes. Most of that extra time went to accessing components the German engineers had deliberately buried beneath protective covers and structural elements. Chen worked through the numbers with slide rule precision, translating those maintenance time differences into operational availability statistics that revealed the hidden toll of engineering complexity. Maintenance time differential represents a 27% reduction in unit availability during sustained operations, he announced, his mathematics showing how design choices affected combat effectiveness through logistical constraints rather than mechanical performance alone. Spark plug replacement offered even more dramatic proof of German engineering priorities that favored theoretical perfection over practical battlefield considerations. The Kubelwagen's horizontally opposed engine configuration buried the spark plugs beneath cooling shrouds and electrical components. Getting to them required partial engine disassembly. What should have been an 8-minute job on any reasonable military vehicle became a 35-minute mechanical expedition that left Kowalski questioning whether those German engineers had ever worked under artillery fire. "This is insane," he said, holding a single spark plug that had required removing 6 separate components just to reach it. "Any farm mechanic in Iowa could service a Jeep engine with basic tools," Kowalski said, his working-class pragmatism bristling against design complexity that served no purpose except demonstrating engineering sophistication to people who would never maintain the equipment they'd created. Major Sterling observed the maintenance evaluation unfold with growing recognition of how engineering decisions translated into tactical capabilities through logistics rather than raw performance. His military education had emphasized keeping equipment operational under combat stress, but what emerged from the Aberdeen workshop revealed fundamental differences in design philosophy that would determine battlefield effectiveness regardless of theoretical capabilities. How do German field units maintain operational readiness with these service requirements? He asked, understanding that maintenance complexity represented a strategic vulnerability Allied forces could exploit through sustained operations. The air filter service provided the final demonstration of German engineering priorities that turned routine maintenance into major mechanical projects. Accessing the filter element required removing engine shrouds, disconnecting electrical cables, and partially dismantling the cooling system. A 25-minute procedure accomplished what American engineers had made possible in 3 minutes through design decisions that prioritized practical service over theoretical optimization. Patterson's documentation revealed patterns extending far beyond individual maintenance tasks, exposing comprehensive differences in engineering philosophy between American and German automotive design. German engineers appear to have optimized for manufacturing efficiency and theoretical performance, while accepting maintenance complexity as an acceptable trade-off, he concluded, his analysis showing how decisions made in peacetime engineering offices would affect operations under conditions designers had never experienced. Chen's mathematical analysis transformed individual measurements into strategic assessments of logistical sustainability under combat conditions. Cumulative maintenance requirements would reduce German unit availability by approximately 30% compared to American equipment under identical operational tempo, he calculated. Understanding these numbers represented the difference between tactical success and logistical collapse during sustained military operations. Cold start testing on December 8 provided final confirmation of German engineering limitations that would prove devastating under actual combat conditions. At 18 degrees Fahrenheit, typical European winter weather, the Kubelwagen's engine refused to start despite 6 attempts following proper procedures. The air-cooled system that eliminated liquid coolant freeze problems created carburation and ignition difficulties that made cold weather operation unreliable when battlefield conditions demanded absolute mechanical reliability. Kowalski watched the American Jeep fire immediately under identical conditions. Its liquid-cooled engine and robust electrical system demonstrated design priorities favoring operational reliability over theoretical efficiency. Game over, he announced. Understanding these measurements represented more than automotive comparison. They revealed fundamental differences in engineering philosophy, determining which industrial system could sustain military operations where mechanical failure meant tactical defeat. As December's testing concluded, the maintenance evaluation had exposed German engineering limitations extending far beyond horsepower specifications into operational sustainability under battlefield conditions. The Kubelwagen represented sophisticated engineering satisfying theoretical requirements while failing practical tests that determined military effectiveness through logistics rather than performance alone. December 15th arrived at Aberdeen with the kind of bitter cold that transformed metal into ice and made every mechanical operation a test of human endurance as much as engineering capability. Kowalski sat in the empty maintenance bay, staring at his completed technical report, while outside the wind howled across Maryland's frozen landscape with relentless persistence, much like German forces were demonstrating across European battlefields despite their demonstrably inferior equipment. Every number in Technical Manual TME 803 told the same uncompromising story. American automotive engineering had achieved measurable superiority over German design in every category that mattered for military effectiveness. 25 horsepower versus 60, 45-minute oil changes versus 12 minutes, hill climbing failure at 8 degrees versus 27-degree capability. The mathematics were irrefutable, documented with scientific precision that would withstand scrutiny from Pentagon engineers who trusted numbers above propaganda or cultural assumptions. Yet American soldiers were still dying in Italian mountains and French hedgerows. Still struggling against Wehrmacht forces equipped with vehicles, Aberdeen's testing had proven inferior to American industrial production. The contradiction gnawed at Kowalski's working-class logic like a mechanical problem that refused to yield to conventional diagnostic procedures. If German equipment was this inadequate, why weren't American forces winning decisively instead of fighting yard by yard through terrain that seemed to favor defenders equipped with demonstrably inferior hardware? Patterson found him there after midnight, the former General Motors engineer carrying 2 cups of coffee, and the weight of his own professional confusion about what their testing had revealed versus what battlefield reports continued to indicate about German tactical effectiveness. "Numbers don't lie," he said, settling into a chair beside the workbench, where months of measurement data lay arranged in neat piles representing the systematic dismantling of German engineering mythology. But they don't explain why Wehrmacht units maintain operational effectiveness despite equipment limitations we've documented. The conversation that followed would later be remembered as the moment when Aberdeen's testing team realized they had been asking the wrong questions about military effectiveness and technological superiority. Chen joined them around 3 in the morning, his slide rule forgotten, as mathematical precision gave way to broader understanding of how warfare actually functioned when human factors combined with mechanical capabilities to produce tactical outcomes transcending simple equipment comparisons. "We've been measuring the wrong variables," Patterson said, his engineering background providing framework for analysis extending beyond horsepower specifications into operational factors determining battlefield success regardless of theoretical equipment advantages. German forces aren't winning because their vehicles are better. They're winning despite having worse vehicles because of superior doctrine, training, and tactical integration that maximizes limited mechanical capabilities. The insight struck Kowalski with the force of mechanical revelation, transforming months of testing data from confusing contradiction into coherent explanation of how military effectiveness emerged from complex interactions between equipment, training, tactics, and operational experience rather than simple technological superiority. German units succeeded because they understood how to extract maximum capability from limited resources, while American forces were still learning how to integrate superior equipment into effective tactical systems. Major Sterling discovered them there at dawn. 3 men surrounded by documentation that had evolved from simple automotive evaluation into strategic analysis of why equipment advantages didn't automatically translate into battlefield success. His military education provided context for conclusions that challenged fundamental assumptions about technological determinism in warfare, while revealing uncomfortable truths about American tactical doctrine that emphasized material superiority over operational effectiveness. German engineering wasn't superior, Kowalski said, articulating insights that months of testing had gradually revealed through systematic measurement of automotive reality versus cultural mythology. It was just different, optimized for mass production under resource constraints rather than performance maximization. They're fighting a poor man's war with equipment designed for efficiency rather than capability. And they're winning because they understand how to use limited resources effectively. The implications extended far beyond Aberdeen's testing protocols into strategic questions about how American industrial might could be translated into tactical advantage on European battlefields where German forces continued demonstrating operational effectiveness despite material disadvantages that Aberdeen's testing had quantified with scientific precision. Superior equipment meant nothing if operators lacked the training, doctrine, or experience necessary to exploit technological advantages under combat conditions. Patterson began drafting supplementary analysis to accompany Technical Manual TME 9803 to Pentagon briefing rooms, explaining how German tactical success, despite equipment inferiority, revealed the importance of training, doctrine, and operational experience in determining battlefield outcomes. American forces possessed superior vehicles, weapons, and logistical support, but German units maintained tactical effectiveness through superior integration of limited resources into coherent operational systems. Chen's mathematical models revealed the strategic implications of Aberdeen's discoveries, calculating how American equipment advantages would eventually overcome German tactical superiority as Allied forces gained operational experience while Wehrmacht units exhausted their trained personnel and logistical infrastructure. The war would be won by industrial capacity rather than individual equipment superiority, with American mass production overwhelming German efficiency through sheer quantitative advantage. As morning light filtered through Aberdeen's windows, the team understood they had documented more than automotive comparison. They had revealed fundamental differences between American and German approaches to military technology that would determine the war's ultimate outcome. German engineering represented sophisticated optimization under resource constraints, while American production demonstrated industrial capacity that could overwhelm efficiency through massive quantitative superiority. The final report emerging from Aberdeen's testing would travel to the European Theatre of Operations as Technical Manual TME 9803, carrying mathematical proof that American equipment was superior to German alternatives across every measurable category. More importantly, it would explain why equipment superiority alone was insufficient for tactical success without proper doctrine, training, and operational integration that maximized technological advantages under battlefield conditions. On June 6, 1944, as 16,000 American jeeps rolled onto Normandy beaches carrying soldiers trained to exploit their equipment, superiority through doctrine that had learned from German tactical success, Kowalski's technical manual provided mathematical confirmation of what D-Day would demonstrate operationally. American industrial might, properly applied through effective tactics, would prove decisive against German efficiency constrained by limited resources and increasingly desperate strategic circumstances that no amount of engineering sophistication could overcome.